Right now, the video you might be watching, or maybe the audio file you're streaming, it's traveling as this rapid-fire sequence of light pulses under the ocean.
Yeah, literally bouncing thousands of times a second inside a glass tube.
Right, a tube that is thinner than a human hair. You tap a piece of glass in your hand, and within milliseconds, a server located on, another continent responds.
It's kind of wild. We completely take it for granted.
We really do. But we are relying on a landscape that is invisible, hyper-complex, and honestly, almost magical.
It is the absolute definition of a modern digital nervous system.
Yeah.
And the sheer scale of it is staggering. I mean,
Yeah.
we have engineered a global substrate that's vastly more intricate than any traditional utility grid.
Yeah, it's a foundational layer for, modern finance, global healthcare, supply chains, literally everything that makes modern world function.
Exactly.
And that is exactly what we are exploring in this deep dive. We are pulling apart the complete guide to Modern Telecommunications Solutions by Ronald Legarski. We're looking at a massive paradigm shift here.
A huge shift, yeah.
Because telecommunications used to be a simple, predictable utility. It was just human voices moving over copper wires. But today, the architecture of the network itself is the ultimate competitive differentiator. Okay, let's unpack this.
If we connect this to the bigger picture, what we are really talking about is a transition from a world of bandwidth scarcity to a world of absolute bandwidth abundance.
Right. Scarcity to abundance.
Yeah, in the legacy era, we relied on circuit-switched networks. You needed a dedicated physical copper path reserved for every single conversation.
So if the copper lines were busy, you just got a busy signal. The network was super rigid.
A closed binary loop, basically. But today, we've transitioned to all IP, packet-switched architectures. Your data, whether it's a voice call, an email, or, a 4K movie, it's fragmented into millions of microscopic packets.
It's chopped up instantly.
Right. Those packets are injected into the network, routed independently through the most efficient global paths, and then reassembled on your device in milliseconds.
So it's kind of like tearing up a 100-page letter, handing each page to a different postal carrier who takes a completely different route across the country. And yet the letter magically reassembles itself perfectly in the recipient's mailbox in the blink of an eye.
That is a highly accurate way to look at it, actually. And it's that packet switch fragmentation that allows us to support massive enterprise operations without the entire system just collapsing under its own weight.
But to understand how this abundance of data actually flies around the globe, we first have to understand what it's connected to on the ground.
The physical layer, yes.
Right, because even in our highly wireless world, the physical foundation of the internet is optical glass. It's an entire photonic highway. We've stopped transmitting electrons over heavy copper cables and started transmitting photons over flexible glass.
Literal light. It's a profound shift in applied physics. I mean, copper suffers from electromagnetic interference and severe signal degradation over distance.
But glass doesn't.
Glass doesn't. But you do run into a different mechanical problem. How do you keep a beam of light inside a transparent glass tube over hundreds of kilometers without it just shining out the sides and leaking into the dirt?
Right, because if I shine a flashlight into a window, the light just passes straight through. How does the data stay trapped inside the cable?
It relies on a phenomenon called total internal reflection. An optical fiber isn't just one type of glass. It has two main layers of high-purity silica.
Okay.
You have the core in the extremely narrow center, and then the cladding wrapped entirely around it. The engineering trick is that these two layers have slightly different refractive indices.
Meaning they bend light in different ways.
Yes, exactly. Because of that difference, when a laser injects a light pulse, which represents a bit of data, into the core at a very specific critical angle, the cladding acts like a perfect mirror.
Oh, wow.
Yeah, the light doesn't pass through into the cladding. It bounces off the boundary. It reflects back into the core, ricocheting continuously, thousands of times per meter.
So it's trapped.
The light is effectively trapped, allowing the data stream to travel tens of kilometers without losing any significant energy.
That is completely wild to think about. Just lasers bouncing down mirrored hallways under our streets. But the source text points out that not all fiber is created equal. There's a big distinction between single-mode and multi-mode fiber.
Right, and the difference entirely comes down to the physical size of that inner core. Multi-mode fiber has a relatively large core.
Okay.
Because it's wider, it allows multiple paths or modes of light to travel simultaneously. The advantage is economic. A larger target means you can use much cheaper, less precise light sources, like LEDs or lower-end lasers.
So it's the absolute workhorse for short, high-capacity hops.
Mm-hmm.
like wiring up servers sitting right next to each other inside an Amazon or Google data center.
Yes, exactly.
Yeah.
But there's a penalty for that wider lane. Because the light rays are bouncing around at different angles, taking slightly different paths, they arrive at the destination at slightly different times.
Oh, see.
Over a long distance, the pulses of light start to spread out and overlap. A clean one in zero turns into this blurry smear of light. This is called modal dispersion, and it corrupts the data.
So multi-mode is out for long distances, which means for those undersea cables or cross-country lines, we have to use single-mode fiber.
And single mode is an engineering marvel. The core of a single mode fiber is microscopic. We are talking 8 to 10 microns in diameter.
That's tiny.
To put that in perspective, a human red blood cell is about 8 microns. The core is so impossibly narrow that it only allows a single ray of light to propagate straight down the center.
Meaning no bouncing around.
Right, because there's only one path, there's zero modal dispersion. The signal stays incredibly sharp, allowing you to shoot data across continents.
I understand the physics of it now, but here's my hang-up. Trenching cables into the earth, securing rights-of-way, laying steel-armored cables across the floor of the Pacific Ocean. That is insanely expensive and time-consuming.
Massively expensive.
And we are consuming exponentially more data every single year. We can't just keep digging up the ground to lay more individual strands of glass every time the world wants to stream more high-definition video.
We can't. The cost would bankrupt the global economy. And that physical limitation is what drove the invention of dense wavelength division multiplexing, or DWDM.
DWDM.
Yeah, this is the true force multiplier of the modern physical layer. Instead of sending one stream of white light down the fiber, DWDM equipment separates the data into highly specific colors, or wavelengths, of laser light.
And it multiplexes them, like it shoots them all at once.
It allows engineers to combine over 80 completely independent channels of data onto a single microscopic fiber pair.
80?
Over 80, yeah. They calibrate these laser wavelengths so precisely that they are spaced as incredibly close as 0.8 nanometers apart. So a single thread of glass is suddenly carrying terabits of data simultaneously.
With completely different networks operating side by side on different colors of light, completely unaware of each other. So if I'm picturing this right, it's like taking a single-lane physical highway and, just by giving the cars different colored headlights, magically turning it into an 80-lane superhighway where no one crashes.
That is a phenomenal analogy. You are essentially virtualizing the capacity of the physical glass. You don't have to dig a new trench to get more bandwidth. You just upgrade the lasers on either end to slice the light into even finer colors.
Which explains a lot. This is why telecommunications companies are obsessed with deep fiber, right? Like FTTX, Fiber to the X initiatives.
Precisely. They want to push that optical glass as physically close to your home or your business as possible, because once the glass is in the ground, it provides virtually unlimited backhaul capacity.
But that brings us to a massive glaring limitation.
Yeah.
We've built this perfectly mirrored underground highway system, but we are a highly mobile society.
We are.
I can't drag a delicate optical glass fiber behind my car, and I definitely don't have one plugged into the smartphone in my pocket. Or think about a robotic arm on a factory sword that needs 360 degrees of rotation. Wires just get tangled and snap. At some point, we have to transmit this data through the air.
You cannot tether a mobile world with glass. And that necessity drives the transition into advanced wireless evolution, specifically the leap from legacy cellular networks into modern 5G and the emerging 6G standards.
Right.
We've reached a point where wireless is no longer a slow, best-effort backup. It is a primary, deterministic conduit.
I think a lot of people just view 5G as the thing that makes my phone download podcasts slightly faster.
Yeah.
But the source document makes it clear that the physics of 5G are radically different from older networks.
Radically different. Previous generations, like 4G LTE, were fundamentally built like floodlights. A cell tower would blast a radio signal in every direction, bathing a massive area in radio waves.
Everyone in that cell sector was sharing the same pool of signal, which means if you're standing in a crowded football stadium, everyone's phone is shouting at the same floodlight, the signal degrades, and nobody can send a text message.
Yes, it was highly inefficient.
Yeah.
5G entirely upends that physics using a technology called massive MIMO, multiple input, multiple output, paired with beamforming.
Beamforming, okay.
Instead of a single powerful floodlight, a 5G base station uses an array of dozens, sometimes hundreds, of tiny antennas. Through incredibly complex signal processing, the tower dynamically calculates the exact phase and amplitude of the radio waves to steer a concentrated, highly directional beam of data directly to your specific device.
Wait, let me stop you there because I want to challenge this setup. If 5G can shoot a dedicated high-speed invisible laser beam of data through the air directly to my phone, why did we just spend the first third of this deep dive talking about glass in the ground? Why not just use wireless for everything and stop digging trenches?
It's a very common misconception, but the wireless network is an illusion. You absolutely require the fiber. Yes. 5G is merely the last mile, or sometimes just the last 100 feet delivery mechanism. Think about the physics of that cell tower. It is simultaneously collecting hundreds of massive gigabit-speed wireless beams from users streaming video, making calls, and running apps.
Right.
The tower itself doesn't process that data. It has to send all of it back to the core internet instantly.
Ah, I see. The tower is just a bridge.
It is a bridge. It relies entirely on that deep fiber backhaul to transport the aggregated traffic. Without a massive photonic highway under the ground connected directly to the base of that cell tower, your high-speed wireless beam instantly hits a bottleneck and slows to a crawl.
That makes perfect sense. But the speed of the connection isn't the only thing that changed, right? Because the source dives into a concept called network slicing, and this seems to fundamentally change how the internet functions on a structural level.
Network slicing is arguably the most revolutionary capability of modern 5G. Historically, a mobile network was one size fits all. Every piece of data, a text message, a YouTube video, a banking transaction, fought for space in the exact same wireless pipe.
Just chaotic traffic.
Right. Slicing allows engineers to take a single physical 5G network and carve it up into multiple isolated virtual networks or slices running side by side in the airwaves.
Here's where it gets really interesting, because you aren't just partitioning bandwidth. You are fundamentally altering the physics and performance rules for each slice based on what the application needs.
That is the crucial distinction. The author outlines three primary categories of these slices. The first is eMBB, or Enhanced Mobile Broadband. This is designed for the typical consumer.
So basically just raw capacity.
Exactly. Its primary directive is raw capacity. This is the wide pipe you need for streaming a 4K movie on a train or using augmented reality glasses.
So eMBB is my massive data pipe. But earlier, I mentioned a robotic arm on a factory floor. A manufacturing plant isn't streaming Netflix. It has tens of thousands of tiny sensors on valves, conveyor belts, and motors. How does the network handle that radically different type of traffic?
That requires the second slice category, MMTC, or Massive Machine Type Communications. The Internet of Things doesn't care about gigabit speeds. A temperature sensor only sends a few bytes of data at a time.
Right, it's just tiny pings.
What it desperately needs is density. The MMTC slice is engineered to support up to 1 million individual connected devices per single square kilometer.
A million.
Up to 1 million, yes. It focuses on low power consumption and high connection volume, allowing smart cities or autonomous factories to exist without overloading the cell tower.
1 million devices in a square kilometer. The sheer scale is difficult to process, but there's a third slice, and this seems like the one where lives are actually on the line.
The third is URLLC, Ultra-Reliable Low-Latency Communications. This slice guarantees deterministic performance. It is hard-coded to deliver data with latencies of less than 10 milliseconds and a reliability rate of 99.999%.
So this is the slice you're using if a surgeon in New York is remotely operating a robotic scalpel on a patient in London.
Yes, or if a fleet of autonomous vehicles is coordinating on a highway. If the lead car slams on its brakes, the signal telling the car behind it to brake cannot be delayed because someone nearby decided to download a massive video file.
So the isolation is that strict?
The traffic isolation is absolute. A massive congestion event on the consumer eMBB streaming slice has zero impact on the URLLC surgical robotic slice, even though they are broadcasting from the exact same physical cell tower.
Okay, but let's pause and look at the picture we've just painted. It is absolute chaos.
Highly complex, yes.
We have 80 different colors of lasers bouncing down microscopic mirrored tubes. We have cell towers dynamically steering invisible radio beams at moving cars. And we are carving virtual isolated networks out of thin air, all with completely different performance rules.
It's a lot to manage.
Human beings cannot manually monitor or route traffic at this speed and scale. If the network relies on a human typing on a keyboard, it crashes. So how does this entirely complex ecosystem manage itself?
That leads us to the final foundational piece, software-defined everything, or SDX, the network brain.
the brain.
To handle the chaos, the telecommunications industry had to completely change how networks are built. Historically, the network logic, the brain deciding where data goes, and the physical hardware, the brawn actually moving the packets, were permanently fused together in proprietary monolithic metal boxes.
Like those massive, highly specialized Cisco or Juniper routers.
Yes. And if an enterprise wanted to change how its traffic flowed or deploy a new security firewall, an engineer had to literally log into individual devices, sometimes physically in the room, and manually type in hundreds of lines of command line code.
That sounds like a nightmare.
It was incredibly slow, deeply rigid, and highly prone to catastrophic human error.
So SDX is essentially decoupling the brain from the brawn. It's like firing all the individual traffic cops standing at every single intersection, manually waving cars through, and replacing them with a single God's-eye view AI traffic system that observes the entire city and controls every stoplight simultaneously.
That is exactly the mechanism. Through software-defined networking, SDN, and network functions virtualization, NFV, the intelligence is extracted from the physical routers and switches.
And moved where?
It is centralized into a software controller. You no longer need to buy expensive, hyper-specialized physical appliances for firewalls or load balancers. You just run them as virtualized software applications on generic, commercial, off-the-shelf servers.
Oh, wow.
The network behaves exactly like a cloud computing environment. It spins up capacity when it's busy and spins it down when it's quiet, autonomously.
I understand the agility of that, but honestly, it raises a terrifying question. If the global telecommunications network is essentially just a giant software application running on generic servers, how does it not freeze or crash?
It's a valid concern.
I mean, consumer software apps crash on my laptop all the time.
Yeah.
We cannot have the digital nervous system of the planet experiencing a blue screen of death.
It is a valid fear, and the industry solved it through a concept called intent-based networking, or IBN, combined with zero-touch provisioning.
Intent-based.
Modern network administrators no longer write scripts telling the network how to do its job. They don't configure individual routing tables. Instead, they define a high-level business intent.
An intent. How does a machine understand an intent?
You program the controller with a policy outcome. For example, prioritize all hospital telemetry data to guarantee sub-5 millisecond latency, and if the network gets congested, offload all guest Wi-Fi traffic to the cheapest available public broadband connection. You just mandate the final outcome.
And the software translates that into the thousands of necessary technical steps.
What's fascinating here is that the AI-driven software dynamically orchestrates the physical hardware across the entire globe to mathematically guarantee that outcome.
That is incredible.
It creates a continuous self-healing loop. The system constantly ingests telemetry data from every single router and fiber link. If an excavator accidentally cuts a fiber cable in London, the AI detects the latency spike in milliseconds, calculates a new path, and autonomously reroutes the critical hospital traffic through Paris before a single data packet is dropped.
It just fixes itself.
It anticipates failures and adjusts before the user ever experiences an outage.
So what does this all mean? We've covered trapped light, precision airwaves, and an AI brain. If I'm sitting at home right now working from my laptop, why does this massive invisible architecture actually matter to my daily life? Why should you care about the infrastructure?
Because telecommunications has fundamentally shifted from being a fixed utility cost to a massive economic multiplier.
An economic multiplier.
The source text references a highly illustrative metric from the World Bank. A simple 10% increase in high-speed broadband penetration yields a 1.2% to 1.5% increase in the entire GDP of emerging economies.
Wow.
We call this the connectivity dividend. When you collapse distance and time using fiber and 5G, you democratize innovation. A small business in a remote village suddenly has the exact same access to cloud computing in global markets as a massive corporation in Manhattan.
And it completely redefines the concept of security and the workplace, too. Because of these interconnected pillars, the source dives into the reality of ACE, Secure Access Service Edge, and ZTNA, Zero Trust Network Access.
Yes, the security paradigm shift.
In the old days, corporate security was a castle and a moat. You went into a physical office building, passed through a physical firewall, and you were trusted. But today, the perimeter is completely software-defined.
Under Zero Trust, your office is wherever you are. Security no longer cares what building you are in. It is permanently attached to your cryptographic identity. The network continuously authenticates you based on who you are, the health of your device, and the context of your request.
And what blows my mind about ZTNA is that it literally makes corporate applications dark or invisible to the public internet. Hackers can't exploit an application they can't even see.
Exactly.
The application doesn't even respond to a network ping unless the user's identity is authenticated first.
Hmm?
It's a completely customized, deeply secure tunnel built instantly across the public internet, just for you.
Providing heavily optimized speeds alongside military-grade security, completely invisibly to the end user.
Okay, let's take a breath and look at the journey we've just taken. To understand the modern world, we started in the ground, trapping microscopic photons in silica glass to create virtually infinite highways of data.
The photonic highway.
We then took that data to the air, using 5G massive MIMO and network slicing to turn wireless networks from a best-effort floodlight into a deterministic precision laser. And finally, we orchestrated the entire chaotic symphony with software-defined everything, an AI-native brain that heals itself and perfectly aligns the physics of a network with your actual business intent.
It is a miraculous convergence of technologies.
Uh,
But as advanced as this all sounds, the source text leaves us with a glimpse into the 6G horizon that pushes these concepts into the realm of science fiction.
Yes, and this is the thought I want to leave you with today to really mull over. As brilliant as our current glass fiber is, engineers are actually hitting the absolute physical limits of how fast light can travel through solid silica. So, their solution, hollow core fiber.
It turns out, light actually travels about 50% faster through empty air than it does through solid glass. So researchers are successfully designing microscopic glass cables that are completely hollow in the center,
Just shooting light through pure air.
shooting data lasers through pure air to shave precious microseconds off global financial transactions and AI communications.
And you combine that hollow core speed with a future 6G wireless network, where the AI doesn't just manage the traffic routing, but actually generates the radio waveforms dynamically in real time based on the immediate environment. We are looking at a near future where the network isn't just a static tool that we use, it is evolving into a living, breathing, self-healing organism.
A fully realized digital nervous system spanning the entire globe.
So the next time you tap a glass screen and a high-definition video loads seamlessly, or a virtual meeting connects you to a colleague across the world, take a brief second. Remember that simple light switch on your wall, and then think about the invisible, hyper-complex, AI-orchestrated nervous system of mirrored glass and focused airwaves that is silently surrounding you, making that exact moment possible. Thanks for joining us on this deep dive. We'll see you next time.